This presentation will address the topic of gas laws and the statistical thermodynamic basis of the kinetic molecular theory. The gas laws might seem like obvious statements in the context of the modern world. But there was a time when molecules were called elementary particles, and evidence of the existence of atoms had not yet been obtained. Because the behavior of gases is predicted with a high degree of accuracy using statistical thermodynamics, many equations are based on the gas laws. For example, the osmotic pressure, as applied to solutions, is just the ideal gas law with one variable renamed. The lowercase I in the osmotic pressure equation is simply a factor that ensures the molar concentration is in terms of the number of particles. For example, when dissolved, sodium chloride forms 2 particles per empirical unit while glucose stays as 1 particle in solution. This is a very important concept to remember. The gas laws, in their ideal form, do not account for the type of particle. What matters is the number of particles. The kinetic molecular theory is used to explain the behavior of gases and is based upon the following postulates. 1. Gases are composed of many particles that behave like hard spherical objects in a state of constant, random motion. 2. These particles move in a straight line until they collide with another particle or the walls of the container. 3. These particles are much smaller than the distance between particles. Therefore, the volume of a gas is mostly empty space and the volume of the gas molecule themselves is negligible. 4. There is no force of attraction between gas particles or between the particles and the walls of the container. 5. Collisions between gas particles or collisions with the walls of the container are elastic. That is, none of the energy of the gas particle is lost in a collision. Under the assumptions of the kinetic molecular theory, we can determine the average force on the walls of a container. The average force and pressure on a given wall depends only upon the components of velocity toward that wall. But the assumption that the molecular motion is random allows us to express these quantities in terms of the average kinetic energy of the particles in a gas sample. Consider a number of identical molecules whose motion follows Newtonian mechanics. The force exerted on a wall perpendicular to the x direction would be the product of mass times acceleration. The acceleration can be expressed as the velocity squared divided by the length of the container. Assuming the motion is random, all 3 directions of motion are equally probable. This allows us to replace the velocity in the x direction with a generic velocity, v squared divided by 3. Then we use the definition of pressure, which is force per unit area. Note that length times area is a volume. After rearranging the equation, we can write it in terms of the average kinetic energy of the particles in a gas sample. When pressure comes up in a question, there is actually 2 of them. We previously derived the pressure of a gas sample in a container. We can call that the internal pressure. But there is also the external, or barometric pressure, named after the barometer. This is the pressure within the atmosphere of the Earth. Its value at sea level is 1 atmosphere. Other commonly used units are the torr and the inches of mercury, used in weather reports, pounds per square inch, used in automotive gauges and industrial machinery, and the pascal, which is the SI unit of pressure. Pressure measures force per unit area. A column of air with a cross-sectional area of 1 meter squared, measured from sea level to the top of Earth's atmosphere, has a mass of about 10,340 kilograms and exerts a force of 101,325 newtons, resulting in a pressure of 101,325 newtons per meter squared. Here are some questions to think about. 1. What are the postulates of the kinetic molecular theory? 2. In the basis of molecular motion, how is the pressure of a gas sample affected by an increase in temperature? But I do not want to bore anyone. So here is this question. A depth charge is detonated by a hydrostatic fuse that measures the pressure of water around the weapon. If the pressure on the hydrostatic fuse is set to 1,500 kilopascals, how deep will the charge sink before detonating? Seawater has a density of 1,050 kilograms per cubic meter, and can be assumed to be a static fluid of pressure given by the product of density times acceleration due to gravity times the height. We set up the equation for the pressure of a static fluid. This is different from a moving fluid, whose pressure is inversely proportional to its speed. If the seawater velocity is assumed to be zero, we have what is called a hydrostatic condition, which means the pressure variation depends only upon the depth of the fluid, the density of the fluid, and the acceleration of gravity. The depth of the seawater is the unknown. We substitute 1,050 kilograms per cubic meter for the density, 9.8 meters per second squared for the acceleration of gravity, and use 1,500 kilopascals, written as 1,500 times 10 to the third pascals. In order to see how the units cancel to give the answer in meters, it is better to write the pascals in terms of the component base units. The unit is named after French scientist Blaise Pascal and is equal to the pressure exerted by 1 Newton of force acting over an area of 1 meter squared. When set up in such way, it is easy to see that all the labels cancel, except for one of the meter labels. The depth we get as the answer is then in meters. Solving for the depth, we get our answer is 145.8 meters. We can conclude that the depth charge will sink about 146 meters before detonating. A depth charge is not intended to destroy a submarine with a direct hit. It is intended to destroy a submarine by being dropped into the water nearby and detonating, subjecting the target to a powerful and destructive hydraulic shock. The underwater pressure wave generated by the explosion is what causes the damage. This is why a depth charge must be set to explode deep underwater. Boyle's idea was to find out how the volume of the gas varied with the external pressure if the temperature of the gas stayed the same. This slide shows the experiment he did in 1662. He trapped the air using mercury in a closed glass tube, taking care so the pressure of the air initially trapped was the same as the atmospheric pressure. He found that if the pressure was doubled, at constant temperature, the gas shrank to half its previous volume. If the pressure was tripled, it went to 1/3 the original volume, and so on. That is, at constant temperature, the product of pressure times volume equals a constant. This is known as Boyle's law. Boyle's law can be verified using a simple apparatus, consisting of a large syringe mounted on a wood block. For illustration purposes and simplicity, let's assume the syringe has a 25 milliliters measurable volume capacity and its cross-sectional area is 1.0 square inches. To make the experiment even simpler, we get wood blocks of equal mass, say 1.0 pounds each. By definition, 1 pound of mass exerts 1 pound of force under the influence of the Earth's gravitational field. If the setup matches our description, then every wood block that is placed on top of the syringe will add pressure in increments of 1.0 pounds of force per square inch. Now we are ready to do some calculations. Consider the Boyle's law apparatus described in the previous slide. Suppose the experiment is done in such a way that the temperature of the gas is kept constant. What is the initial pressure of the 25 milliliters of air? How many 1.0 pound woodblocks will it take to compress the air to a volume of 20 milliliters? To answer the first question, we need to understand the concept of absolute pressure. This quantity is equal to the barometric pressure plus the gauge pressure. Initially, no woodblocks have been added on top of the syringe. At this point, the pressure inside the syringe is equal to the pressure outside, that is, the barometric pressure. The standard value for this quantity is 1 atmosphere, which is equal to 14.7 pounds of force per square inch. The absolute pressure will increase once the wood blocks are added. To answer the second question, we can use Boyle's law with initial pressure set to 14.7 pounds of force per square inch, and the initial volume, 25 milliliters. By setting the final volume equal to 20 milliliters, we get the final pressure, 18.38 pounds of force per square inch. Any unit of pressure and volume can be used for Boyle's law. The units just need to be consistent. We can convert the 18.38 pounds of force per square inch to atmospheres, using the conversion factor. 1 atmosphere is equal to 14.7 pounds of force per square inch. The answer is not exact in terms of the number of woodblocks required to produce the required gauge pressure of 3.68 pounds of force per square inch. To compress the 25 milliliters of air to a volume of 20 milliliters, You would need to put 3 blocks of wood plus some other object that weighs about 11 ounces. Around 1787, Jacques Charles did an experiment where he filled balloons to the same volume with different gases. He then raised the temperature of the balloons to 80 degrees Celsius and noticed that they all increased in volume by the same amount. He concluded that the volume of a gas at constant pressure increases linearly with the absolute temperature of the gas. The figure on the bottom left of this slide shows what Charles' experiment setup may have looked like. A glass bottle and a balloon could have been filled up with gas. By placing the bottle in water at room temperature, the gas sample would reach thermal equilibrium with the water. When the water was heated to 80 degrees Celsius, the gas would also attain a temperature of 80 degrees Celsius. Because the gas expanded against the Earth's atmosphere, the pressure can be assumed to be whatever the barometric pressure is the day of the experiment. The barometric pressure does not change significantly over the time frame of such an experiment. Jacques Charles did not publish his work, but the results were later reviewed by Gay-Lussac, who credited Charles' work and named the law in his honor. Gay-Lussac also formulated Gay-Lussac's law, stating that if the mass and volume of a gas are held constant, then gas pressure increases linearly as the temperature rises. But Gay-Lussac was an adventurer. In 1804, he made a hot air balloon ascent with fellow scientist Jean-Baptiste Biot. They reached a height of 23,000 feet so that they could study the Earth's atmosphere. This was a time before parachutes and health insurance. As a practical example, consider Gay-Lussac's hot air balloon, which has an envelope that can hold 2,500 cubic meters of air. Suppose the gondola plus the envelope have a mass of 500 kilograms and the combined mass of Gay-Lussac and Jean-Baptiste Biot is 150 kilograms. To what temperature must the air inside the balloon be heated before it will start ascending? Assume the pressure is constant and the density of air at the initial temperature of 20 degrees Celsius is 1.3 kilograms per cubic meter. It may not seem obvious at first, but we can use Charles' law combined with Archimedes' principle to solve this problem. Raising the air temperature inside the balloon reduces its density. The buoyant force, according to Archimedes' principle, is the weight of air displaced by the balloon. It all comes down to a simple density calculation, followed by Charles' law. We can start by computing the mass of air displaced by the balloon. Using the density equation, we conclude that a 2,500 cubic meters balloon displaces 3,250 kilograms of air. The density of air inside the balloon must decrease so that the combined mass of hot air, the envelope, the gondola and the 2 passengers is less than 3,250 kilograms. Using the given parameters, we find that mass must be less than 2,600 kilograms. Because Charles' law has volume as a variable, we must obtain information about the volume from the density. We compute the density of hot air inside the balloon. This comes up to 2,600 kilograms per cubic meter. From the density formula, we get that for a constant mass, the volume is inversely proportional to the density. This means we can get the air expansion ratio from the density ratios. Using this rationale, we conclude that the hot air must expand at least 1.25 times compared to its volume at 20 degrees Celsius. We are now ready to use Charles' law, but hold your horses, or camels if you are into that kind of thing. Charles' law accepts any volume unit, but the temperature must be in Kelvin. The 20 degrees Celsius becomes 293 Kelvin, and now going to Charles' law. For the volume at 293 Kelvin, we use 2,500 cubic meters. For the volume at the unknown temperature, we use 1.25 times 2,500 cubic meters. The first step on Charles' law is computing a constant with units of volume per Kelvin degree. Then use the constant as a conversion factor between the known volume and the unknown temperature. We get our answer as 366 Kelvin, which is equivalent to 93 Celsius degrees. We can conclude that the balloon, carrying Gay-Lussac and his friend, will start ascending when the temperature inside the envelope goes above 93 Celsius degrees. Charles' law can be verified by determining the volume of air at 2 different temperatures. The volume at the high temperature is equal to the volume of an Erlenmeyer flask with a rubber tubing attached. The flask is submerged in hot water, and the rubber tubing is submerged under ice water in a separate container. When bubbles stop coming out of the tubing, the air has expanded to its high temperature volume. The flask is then submerged under the ice water, and the air contracts to its low temperature volume. The contraction of air creates a pressure gradient that draws water into the flask until the pressure inside the flask equalizes with the barometric pressure. The low temperature volume is computed by subtracting the volume of water drawn into the flask from the high temperature volume. Charles' law also yields another, even more interesting result. Charles must have measured the temperature using the Celsius scale. The change in volume divided by the change in temperature is the slope of a straight line equation, and its value is the compression or expansion factor of the gas sample. If we substitute the data for the variables in the equation, y equals mx plus b, where y is equal to the volume of the gas, and solve for the temperature when the volume goes to 0, then we get a value that is very close to minus 273 Celsius. This is known as absolute zero, the lowest temperature possible, and the 0 point in the thermodynamic temperature scale, a state at which the enthalpy and entropy of a system of particles reached their minimum value. Avogadro's law is what unifies empirical data in the kinetic molecular theory. This law states that equal volumes of all gases, at the same temperature and pressure, have the same number of molecules. The law implies that, under constant temperature and pressure, some chemical reactions can result in a volume change, even though the mass is not changing. Take for example, 1 kilogram of oxygen at certain temperature and pressure, converting into ozone, at the same temperature and pressure. According to Avogadro's law, the volume of ozone will be 2/3 of the volume of oxygen used to produce it. To illustrate the implications of Avogadro's law, consider two enclosures of equal area. The one on the left is occupied by 6 hippos. The one on the right is occupied by 6 pigs. The hippo enclosure is a bit crowded. After all, a hippo is much larger than a pig. Molecules also differ in size. And that brings the question: is Avogadro's law saying that a molecule of acetone fits in the same space as a molecule of hydrogen? Well, actually, no. Now, suppose we make the enclosures larger. Now each side of the enclosure is 50 times longer. Now, the hippos and the pigs do not look so different in terms of size because the area of the enclosure is much larger than the area each animal occupies. This brings us back to one of the postulates of the kinetic molecular theory. Gas particles are much smaller than the distance between them. Therefore, the volume of a gas is mostly empty space and the volume of the molecules themselves is negligible. The ideal gas law is an equation of state that is very important and fundamental in thermodynamics, and was first proposed in 1834 by physicist and engineer Benoit Paul-Émile Clapeyron. The ideal gas law is a good approximation to the behavior of many gases, although it has limitations. The first iteration of the ideal gas law combined the results of Jacques Charles, Robert Boyle and Gay-Lussac. The equation simply says that the ratio of pressure times volume to temperature is a constant. As is known today, the equation includes the universal gas constant. Another addition is Avogadro's law, which acts as a proportionality constant to account for the fact that each gas has its own molar mass. Just a reminder, the ideal gas law does not have a mass parameter. One molecule is one molecule no matter what its molar mass is. Avogadro's law can be verified with a simple experiment, which consists of allowing a small volume of a volatile liquid to vaporize inside an Erlenmeyer flask. The mouth of the flask is covered with aluminum foil and a small hole is punched in the foil. The flask is placed in a hot water bath. As the liquid evaporates, the pressure exerted by the gas increases and the excess vapor will escape through the pinhole until the pressure of the gas equalizes with the barometric pressure. The gas is allowed to condense and the remaining liquid is weighted. According to Avogadro's law, we can compute the mole of gas from the experiment's data. As a practical example, suppose you perform the previously described experiment to verify Avogadro's law. The volume of the Erlenmeyer flask was found to be 156.6 milliliters and the barometric pressure reads 757 torr. A small volume of acetone vaporized inside the flask at a temperature of 95 degrees Celsius. The remaining vapor is condensed and its mass is found to be 300 milligrams. Compute the molar mass of acetone. The molar mass is the number of grams divided by the number of mol. From the ideal gas law, we can get the number of mol of vaporized acetone. But first, the pressure must be in atmospheres, the volume must be in liters, and the temperature must be in Kelvin. Then we substitute the variables in the ideal gas law. The pressure equals 0.993 atmospheres. The volume equals 156.6 times 10 to the minus 3 liters. And the temperature equals 368 Kelvin. For the constant, R, we use 0.0821 liter times atmospheres per mol times Kelvin. This gives our answer as 5.15 times 10 to the minus 3 moles. Finally, we divide the mass of condensed acetone by the number of mol. This gives our answer as 58.3 grams per mol. This is very close to the molar mass of acetone. Here are some questions to think about. 1. Define absolute pressure. How does it relate to gauge pressure and barometric pressure? 2. What is the connection between Charles' law and the thermodynamic temperature scale? But if you prefer something more interesting, here is this one. Consider a piston and cylinder assembly with 2.5 centimeter bore diameter. Compute the mass of the piston if its weight compresses the air inside the cylinder to 97% of its original volume. Assume the temperature stays constant. First, we approach this as a Boyle's law problem, setting the initial pressure equal to the barometric pressure, which is 1 atmosphere, with initial volume equal to V. We can solve for the absolute pressure by setting the final volume equal to 0.97 times V. Then we can obtain the gauge pressure by subtracting the absolute pressure, which is 1.031 atmospheres, from the barometric pressure, which is 1 atmosphere. After doing the math, we conclude that the force exerted by the piston results in 0.031 atmospheres of gauge pressure. Because our objective is obtaining the mass of the piston, we must first compute the force exerted by the piston. For this, we need to convert the pressure into standard SI units. We use the conversion factor. 1 atmosphere is equal to 101,325 pascals. The answer, 3.141 times 10 to the third pascals, can also be expressed as 3.141 times 10 to the third newtons per meter squared. So we can compute the force exerted by the piston if we know the area of the head of the piston. After doing the math, we conclude that the head of the piston has an area of 4.91 times 10 to the minus 4 meters squared. Then we use the definition of pressure, which is force per unit area, to obtain the force exerted by the piston. This force is the product of mass times acceleration on the Earth's gravitational field. After doing the math, we conclude that the piston has a mass of about 157 grams. This result is obtained by assuming that air is an ideal gas. But those paying attention may be asking themselves the following question. What about the hippos and the pigs? The reality of the matter is, these animals and any other physical being still has a volume that cannot just disappear. Theoretical physicist Johannes Diederik van der Waals also asked himself the same question and concluded that molecules occupy a finite volume. The picture at the center of the slide shows what is called the van der Waals volume of a molecule. We normally draw molecules as if they were made of atoms connected by sticks. Actually, molecules are very fluffy, and the combined volume of constituent atoms result in what is called a van der Waals surface. In extreme conditions, the ideal gas law may break down as some of the assumptions relating a real-life example to an ideal gas become untrue. Then the definition of an ideal gas will contrast with the non-ideal gas definition, because this equation represents how a gas actually behaves in reality. Under such conditions, the ideal gas law is replaced with the van der Waals equation, and two main corrections are made to the kinetic molecular theory of gases. 1. The particles have forces acting among them. These forces become more influential as the number of particles per unit volume increases. 2. These particles take up some space, and their excluded volume adds up in proportion to their size and number. At low pressure and high temperature, the ideal pressure and the van der Waals pressure are nearly identical because the particles are so far from each other that attraction between them is ignorable. Also, the volume of all particles in the gas is small compared to the volume of the container. As a result, the ideal volume and the van der Waals volume are nearly identical. At high pressure and low temperature, the molecules that exert the force on the container will get attracted by molecules of the immediate layer which are assumed not to be exerting pressure. This will lessen the impact of the molecules striking the wall of the container, and the van der Waals correction factor cannot be ignored. Also, the combined volume of all particles is comparable to the volume of the container, and the van der Waals correction factor cannot be ignored. We can conclude that the ideal gas law will break down under extreme conditions that are likely to amplify the effect of particle-to-particle interactions in excluded volume. We conclude this presentation with some questions to think about. 1. What are the main corrections to the kinetic molecular theory that are introduced by the van der Waals equation of state? 2. Looking back at the Avogadro's law experiment to determine the molar mass of acetone. Compute the excluded volume assuming the volume of liquid acetone is a good approximation for the volume of the constituent molecules in the sample. But some of you may find those questions to be a bit simplistic. So here is this one. Consider a hipster, high in the Himalayas, where the temperature is -45 degrees Celsius and the barometric reading is 0.635 atmospheres. Compute the density of dry air in grams per liter. Under those atmospheric conditions, dry air has an average molar mass of 28.9 grams per mol. Will this hipster pass out from lack of oxygen at this altitude? The minimum required oxygen partial pressure for a hipster to remain conscious is about 115 torr. Just so you know, the normal partial pressure of oxygen at sea level is about 160 torr. You can pause the video and try it. One hint as to how to approach this problem is to use the ideal gas law and think outside the box. Or barrel, if you are into that kind of thing. I have decided to provide the answer to these questions. After all, what are the odds of finding honorable people in this world? We use the ideal gas law. The equation has amount in units of mol, and volume in units of liter. Putting those two units together, we can get concentration in mol per liter. Then we can convert concentration to units of grams per liter using the average molar mass of air, which is 28.9 grams per mol. After doing the math, we get our answer as 0.98 grams of air per liter volume. Just so you know, under normal atmospheric conditions, the concentration of dry air at sea level is about 1.2 grams per liter volume. Air is a mixture of several gases. The two most dominant components in dry air are 21% oxygen and 78% nitrogen. The other 1% is made of mostly trace amounts of noble gases. This percent composition is in terms of volume, and according to Avogadro's law and Dalton's law of partial pressures, this percent composition is also the mole fraction of each gas. Using this rationale, the partial pressure of oxygen is the barometric pressure times the oxygen concentration. Air always contains the same relative concentration of constituent gases, but the air gets thinner at high altitude. We can use the conversion factor, 760 torr is equal to 1 atmosphere, to convert the partial pressure of oxygen from atmospheres to torr. Our final answer is 101 torr, which is well under the oxygen levels required for the average hipster to remain conscious. We can conclude that this hipster is going to pass out from lack of oxygen, and will need a Sherpa to drag him down the mountain, either dead or alive.